So am I audible?
Yes, sir.
Okay, so up to last class, we have finished this term, motional EMF, right? This was the last numerical that we did, minus of half B omega L square. Please check your notes. Is this the last numerical that we did, minus half B omega L square? Please check your notes. Is this the last topic, last numerical that we did? Yashika, Nabil, Akshay, Minashi. Is this the last numerical that we did in Lenz's law?
Yes, sir.
Okay, this was the last numerical. So that's Lenz's law. After Lenz's law, the next topic is okay. There are few more numericals that we should do. We did this numerical, no? Okay. The next question that we should do is note down this question. This is again based on Lenz's law, particularly on the rotating coil. Just note down this question. It's a very, very important question. At the end of the question, just write, this is the principle of AC dynamo also. This is also the principle of AC dynamo. Yes. Have you written the question?
Writing, sir.
1 minute, sir.
Tell me once you have written. I'll start something. Okay. Written question? Yashika, Noha?
Yes, sir. Sir, right.
Okay, so let's start the solution. So you have a coil. This coil is rotating in a magnetic field. It rotates about its diameter with an angular velocity omega. You have to calculate EMF induced in the coil. So EMF will induce in the coil only if the flux linked with the coil change. This is the Faraday's law. Faraday's law says the EMF will induce in the coil only if the flux linked with the coil change. What is the formula to calculate flux, Hishma? Hishma, what is the formula to calculate flux?
NBA cos theta.
Very good. PA cos theta. So you have to decide, due to the rotation of coil, which quantity will change? If nothing is changing, that means there is no change in flux and EMF will be zero. So first of all, you have to decide that due to the rotation of the coil, which quantity is changing? B is changing, A is changing, or theta is changing. So just for the sake of your convenience, let's say this is the coil. This is the diameter of the coil. This line, I call this line as the diameter of the coil. This coil is rotating in this way. And this is the direction of magnetic field. This is the magnetic field. I need something else. This is the magnetic field. This is the area vector of the coil. This, or you can say that this is magnetic field in the inverse direction, and this is the area vector of the coil. Can you tell me what is the angle between the area vector? This is magnetic field inverse, and this is area vector right now. What is the angle between area vector and magnetic field? Everyone, please just unmute your mic and tell.
90 degrees.
90 degrees.
Zero.
Zero.
Degrees.
Magnetic field is inverse, area vector is also inverse, angle is zero. Magnetic field remain as it is. Now the coil starts rotating. What's the angle between magnetic field and area vector now?
90.
90 now. Now it
90.
goes in this way. It's
180.
coming out 180,
180.
then 270, then 360, then again 90, then 180 and all.
Then zero.
So due to the rotation of the coil, which quantity is changing? B is changing, area is changing, or theta is changing?
Sir, theta, sir.
Theta.
Theta is changing, which means your flux is changing, right? So due
Sir,
to change in
area vector is along the
perpendicular to the area. So area vector is perpendicular to the area.
sir, it is outwards from the coil, sir, long radius.
For this particular coil, this coil is placed in YZ plane. So this is the area vector right now. This is area vector along x-axis. But when it rotates, the angle between area vector and magnetic field will change, right?
Yes, sir.
So the coil, according to the diagram, this is the magnetic field and your coil is placed in this way. This is the magnetic field and your coil is placed in this way. This is the direction of area vector. So what's the angle? Angle is 90 degrees. Okay.
Yes, sir.
Sir, can you explain? Can you give a brief?
Yes, yes. We are doing this numerical. So this is magnetic field, which is in the inverse direction. And in this magnetic field, a coil is rotating. So I'm trying to explain that due to rotation of the coil, the angle between the magnetic field and the area vector is changing. The thing is, the magnetic field is inverse. Let's say take this pen as the magnetic field. This is the area vector. Initially, your coil is in this way. So the angle between magnetic field and area vector is zero. Now, when your coil rotates, the angle changes. It becomes 90 degrees. When it rotates more, the angle becomes 180 degrees. Then angle becomes 270. Then it becomes zero again. So due to the rotation of coil, the angle between the magnetic field and area vector is changing. Right?
Yes, sir.
So flux is changing due to change in theta. Now, we can write angular velocity in terms of angular displacement also. So omega is the angular velocity. So you can write that angular velocity omega is equal to angular displacement divided by time. Or you can say that your angular displacement is angular velocity multiplied by time. Let's call this as equation number 1. Let's call this as equation number 2. Now, when you substitute 2 in 1, I get phi is BA cos omega t. This is flux, BA cos omega. So flux change with time. When time changes, flux changes. You can calculate induced EMF also. What is Faraday's law, Nabil Khan? Where is Nabil? Nabil Khan. Yes, Nabil. Nabil, what is Faraday's law?
Sir, induced EMF in a coil is equal to the change in magnetic flux.
Very good.
produced
So,
in the coil.
yeah, so induced EMF is not just
That is
change, rate of change.
proportional to the rate change.
Rate of change. So it's minus of d over dt of phi. Phi is BA cos omega t. Yashika, what are the constant terms in this derivative? What terms are constants here?
Sir,
Hmm.
A,
Okay, good. See, area is constant due to rotation of coil. Area is not changing. So area is constant. And what about the magnetic field, Yashika? See, it's placed in a uniform magnetic field.
sir, not changing.
Magnetic field is not changing. B is not changing. Area is not changing. Only the time is changing. Just have to differentiate cos omega t. Is there anyone in this batch who doesn't have maths in class 12 as a subject? Anshika, you have maths?
Sir,
You don't have maths. Okay. So see, this is minus of BA. You have to differentiate cos omega t. So Arpit, the derivative of cos omega t is minus of sine omega t. Fine. The derivative of cos is minus sine. But see, along with the time, you're also getting omega. Along with the time, you're also getting omega. So you can take this omega outside. I'm repeating it again. You're differentiating cos omega t. The derivative of cos omega t is sine omega t. But along with t, you have a constant omega. That's multiply with omega. So your EMF
We
will
can
become
cancel omega, right?
from where?
We can cancel omega.
Why? Why will cancel omega? Nabil? Nabil, it's your doubt. Just tell me why you think that omega will get cancelled out.
So we
Nabil,
can add it at the end, right?
yeah, it get added in the equation at the end, but it got cancelled. So when you differentiate cos, the derivative is minus sine. But if you have a constant along with t, that constant will come outside the derivative. So it's BA omega sine. Is it clear?
Yes.
Yes, sir.
Okay, Minashi don't have maths. Alia don't have maths. Minashi, Alia, and Arbit. Is it clear now? You're
yes.
differentiating cos omega t, it's minus of omega sine omega t. So that is the EMF. Okay, what type of EMF is this, Arpit? Is it a constant EMF or a variable EMF?
Sir, it will vary.
Why? Why, Arpit, it will vary?
Sir, according to the value of the sign.
Because it depends upon time, right?
Yes.
It depends upon time. So when time changes, EMF will change. So it's a variable EMF. It is a variable EMF. The EMF
Omega will
will...
remain constant, sir.
Sorry?
Sir, omega will remain constant.
Yeah, omega will remain constant. The angular velocity is constant. Angular velocity is not changing. But due to the change in time, time will change. So EMF will change. Now, if you want, you can plot E versus time graph. The graph, okay, first, before plotting the graph, let's calculate the maximum value of EMF. Maximum value of EMF. So see, EMF depends upon sine omega t. When this EMF is maximum, for what value of sine omega t is this EMF is maximum? Tell me.
90.
90. So for maximum value of EMF, sine of omega t plus b plus 1. So if you take sine omega t to be plus 1, so your EMF will be BA omega. So this is your EMF, BA omega. When this is the EMF when your sine omega t is 1. This is the maximum value of EMF. So if you want to plot EMF versus time graph, this is time and this is EMF. Now, since this EMF have this sine omega t term, that means the function is sinusoidal. The graph will be that of sine theta. This is the standard plot of sine omega t. This is sine omega t. This is the maximum value, Emax. So this is how your EMF will vary. Your EMF will be 0, then it will become maximum, then will again become 0, then it will become negative. In negative, the value will be minus of maximum. Then it will again become 0. From here to here, the time is capital T. Capital T is the time period. When I say time period, that means time taken to complete one rotation. Means if I take example of this mobile phone, then the time taken by this mobile phone to rotate from here to here again, to complete one rotation, is the time period. So if you look at the value of EMF, that means in a single time period, it becomes 0, then it becomes maximum 0, negative, and then again it becomes 0. This time is T/2. This time is T/4. After 1/4 rotation, your EMF is, this is T/4. Oh, sorry, 3D/4. This is the graph. So this is EMF versus time graph. Again, from where I'm getting the shape, I can plot this shape also, but those who doesn't have maths, remember this shape. This is standard sine curve. In class 11th also, in SHM and waves, you must have drawn this curve several times. The standard sine curve. This is standard sine curve. The time taken for one rotation is T, so I know that this is T. This is half, so I make it T/2. This is half of T/2, so I make it T/4. And this is in between T/2 and T, so I call it as 3T/4. This is how I'm deciding the time. So by looking at this EMF, this plot, I can say that at T equal to 0, your EMF was 0. At T equal to T/4, your EMF becomes maximum. At T equal to T/2, your EMF becomes 0 again. Then at 3T/4, your EMF is negative now. And at T equal to capital T, your EMF becomes 0 again. So this is standard EMF versus time graph. Okay, we can do few more things here. We can ask you to calculate the average value. Huh? He can ask you to calculate average value. So here, the method of calculating average is a bit different. If I give you numbers, like I give you 2, 3, and I give you 5, and I ask you to calculate the average. So just 2 plus 3 plus 5 divided by 3, it's 8/3, 10/3. For average value of EMF, what we can do is we take the average. I'm just teaching you the shortcut to calculate average value of these type of functions. This is BA omega sine omega t. This is the symbol of average. Huh? I have to calculate the average value. No. While calculating average, the terms which are constant can be taken outside. So what terms are constant? B is constant, A is constant, omega is constant. So you can take B outside, you can take A outside, you can take omega outside, and you have just sine omega t. To calculate the average of sine omega t, what we will do, we will first take the minimum value of sine omega t. Akshay, what is the minimum value of sine omega t?
0.
No.
Oh, -1.
-1. Maximum value +1 divided by 2. So it will be 0. So the average will be 0. It's a variable EMF, but if you calculate the average value of this EMF, it comes out to be 0. And this 0, average is 0 is clear from this plot also. This is positive, this is negative. Both positive and negative are barabar, equal. So you can say that they should cancel each other. Just note it down and tell me if you have doubt in any step. Don't just copy the calculation. Please do it yourself. When you're stuck somewhere, discuss. Discuss with me. If something does not satisfy your logic, just tell. Yes, Nabil.
Flux linked with coil means that magnetic flux by the external source that is linked to the coil.
Can you just please repeat, Nabil? Your voice.
So the flux linked with coil means the external magnetic field that is linked to the coil.
Yeah, the external magnetic field which is passing through the coil.
सर ये AC का पार्ट है या फिर EMI का ही?
EMI. But we will start AC dynamo from this calculation. This is the case which leads to AC dynamo, and your AC starts from this calculation. This, by the way, this is your homework question. The last week I gave you three numericals in homework. 3 or 2? Yashika.
One example, two exercises, sir.
2 questions, huh? This is your homework question.
Sir,
basically.
can you show the figure? Yes, sir.
सर ये जो वाइट में ये सेम लिख
हाँ सेम है, इसको मत करो, ये लास्ट ईयर का. Everything is same. There's no change in steps. Last year also the timings were same, syllabus was same, only some few students were different. So almost like last year also I had 9-10 students in the batch. On those 9-10, I believe some 7 or 6 students have scored more than 90% physics.
Sir, could you scroll down, sir?
Yes. See, please share the question paper of your sessional exams on the group, please. Just so that others can use it as a reference. Just take the photograph, convert it to a PDF and share it on the group.
Sir, are there assignments in the website, sir?
There should be. Basically, I don't give assignment when I'm teaching first book. I give assignment as a revision. First, let me finish this chapter, this AC, then we will start the revision through assignment.
Yes, sir, because when I checked the assignment section, many of them are expired, sir. I didn't
Okay.
even know they were published in the first
So,
place.
no, you won't be. You must be having assignments of other subjects, but not of my subject at all. Because when the first book gets completed, that means 70-75% syllabus is over. Then we'll do the revision of the first book and second book.
Sir, what is it, sir? E m infinity is equal to B A omega.
Where
Maximum value of EMF, sir. Under that, this yellow box.
E max is BA omega. E max is BA omega. It's not infinity. E max, the maximum value of EMF is BA omega.
Yes, sir. Sir, this means that maximum EMF is induced when the area vector is perpendicular to the magnetic field, sir.
No, when the area vector is parallel to the magnetic field. Because it's at T/4, no? Initially, it's equal to 0. So that means initially your area vector is perpendicular to magnetic field. The coil is starting from this configuration. This is the magnetic field. This is the coil at T equal to 0. So that angle between magnetic field and area vector is 0. That's why you can see that at T equal to 0, your EMF is 0. Then it rotates. By 90 degree, it rotates and your EMF becomes maximum. So your EMF is maximum when the angle between the magnetic field and area vector is either 0 or 180.
Sir, but sine of 30 is 1 means then the angle should be 90, right, sir?
But this angle is not the angle between area vector and magnetic field. This is omega into T. You can write this as 2 pi by capital T into small t is equal to pi by 4. So this is not just the theta angle between magnetic field and area vector. This is related to the time. Omega, you can write it as, see, omega t is 90. No? Or you can say that omega t is pi by 2. You can write your omega as 2 pi by capital T and then small t, which is equal to pi by 2. So your t become t by 4. So after t by 4th time, your is maximum. Remember, EMF and your flux have different phases. So when you calculate flux, this is cos theta. It was cos omega t. But when you are writing EMF, it's not cos, it's sine. So it's not the same angle as was in flux. This omega t here is not this omega t, the angle between area vector and magnetic field, because you have differentiated it one time. There's a phase difference between. So the question that you were asking that it's 1 means angle is 90 degree. Angle is 90, but it's not the angle between magnetic field and area vector. Written, everyone?
But this is not alternating current.
Yes, this is alternating EMF. This is the source of alternating EMF.
Yes, sir.
That's why I wrote this is the principle of AC dynamo. This is the source of alternating EMF. Everyone have written? Can I slide it over?
Yes, sir.
Sure. So this completes our motional EMF. The next is mutual induction. See, what does mutual induction means? To understand mutual induction, let's understand this diagram first. So you have two coils, coil 1 and coil 2. So you can see that coil 1 is connected to a cell. Coil 1 is connected to a cell, and for coil 2, there is no cell. There is no cell of EMF. There is no cell of current. The coil 2 is only connected to a galvanometer. So if you if you look at this diagram, there should not be any current in the galvanometer because there is no source of current in this coil 2. The source of current is cell. There is no cell, so there should not be any current in the galvanometer. So mutual induction says when you close this key, then current in this coil will increase. In coil 1, current will increase. Coil 1 will generate its own magnetic field. Coil 1 will be generating its magnetic field now. The magnetic field generated by coil 1 is B1. Coil 1 is generating its own magnetic field. That magnetic field is passing through coil 2. So there is some flux linked with coil 2. And what is that flux? That flux is magnetic field of first coil multiplied by the area of second coil. So what is the cause of flux linked with second coil? It is the magnetic field of first coil. Now, if this current is increasing, that means this magnetic field is also increasing, which means this flux is also increasing, which means flux linked with the coil 2 is changing. If the flux linked with the coil 2 is changing, that means some EMF should be induced in coil 2. If you have induced EMF here, then you should have induced current because it's a closed circuit. Coil 2 is in a closed circuit. So if it have induced EMF, then it will have induced current also. So your galvanometer will show some deflection. If you think, then what is the cause of that deflection? The cause of that deflection is not coil 2. The cause of that deflection is the current of coil 1. So the changing current of coil 1 is inducing a current in coil 2. This is known as mutual induction. You change current in one coil and current gets induced in the another. This is what we call mutual induction. And this plays a very, very significant role in transformers. Transformers or stabilizers that you have, that they are based on this concept of mutual induction. Is it clear, everyone, what is mutual induction exactly?
Yes, sir.
Yes, sir.
You change current in one coil and you get induced current in the another coil. This is mutual induction. Now, to develop theory of mutual induction, we need few quantities. Whenever current in one coil changes, an EMF is induced in every coil. So let me write this thing again. Flux linked with coil 2 is proportional to current in coil 1. This is that we have discussed here. This is the thing that we have discussed here. So you can say that phi 2 is directly proportional to I1. If I remove this sign of proportionality, then I use a coefficient M21 I1. This M21 is known as coefficient of mutual induction of coil 2 due to coil 1. This basically means EMF gets induced in coil 2 due to current of coil 1. That is M21. Now, this M21 depends upon various factors. It depends upon the geometry of the coil 2, because it's obviously flux now. Flux depends upon the area of coil 2. So it depends upon the area of coil 2. It also depends upon the separation between the coils. Because if you increase the separation between coil 1 and 2, then magnetic field will decrease, strength of magnetic field will decrease, flux will change. So it also depends upon the separation between the coils. You can say your coefficient of mutual induction depends between separation, it depends upon orientation, it depends upon geometry, and also the nature of material. Because if you change the material, then magnetic field will change. So this is mutual induction of coil 2 due to 1. Okay, can you just tell me in which coil current is inducing, in coil 1 or in coil 2? Which coil will have induced current?
Coil
Two, sir.
2,
Coil 2. And what is the cause of that induced current?
the current in the coil.
Change in magnetic field due to
Yeah,
coil 1.
Or you can say that changing current in coil 1. The current which is changing in coil 1 responsible for the induced current in coil 2. In general, you can write this as phi is equal to mi. And when you apply Faraday's law, you can write few terms. Just give me one. Arpit, what is Faraday's law? Arpit. Arpit is not in class. Hishma, what is Faraday's law? What? Faraday's law.
Sir,
Just 1 minute, Nabil. Nabil, 1 minute. Just 1 minute. Hishma,
Yes, sir.
what is Faraday's law? Faraday's law of electromagnetic induction. Okay. Anshika was absent in the last class. I would ask Anshika. Uneeb, what is Faraday's law? Faraday's law of electromagnetic induction, right, Alia? Uneeb. Yoshika, what is Faraday's law of electromagnetic induction?
So change in magnetic field creates a flux.
Yeah.
Induces EMF in the circuit. So
Changing magnetic flux induces EMF. So using Faraday's law, you can say that E is minus of d phi by dt. So what you can do is you can substitute the value of phi here. So it will be minus of d over dt of mi. Now, m depends upon these factors. These factors are not changing. Separation is not changing. Orientation is not changing. You're not rotating the coils. You're not changing the geometry. You're not changing the nature of material. This m is a constant. So you can take this m outside your derivative. It's m minus m di over dt. So this is induced EMF minus of m di over dt. This is the formula for induced EMF. Next, when you write the SI unit of m, so you can say that E is m di over dt. So you can say that m is E by di over dt. So what is the SI unit of E?
sir, volts.
Volt. And it's di over dt. It's current by time. So it's ampere per meter. So that is the SI unit of M. So you can say the SI unit of M is volt meter per ampere. And this is known as Henry. This is also known as Henry. The SI unit is Henry. Volt meter per ampere is the Henry. Henry is the SI unit. And this negative sign again shows Lenz's law, that the direction of induced current will oppose its cause. This negative sign again is the Lenz's law. So let's recall it again. What is mutual induction? Change in current in one coil will induce current in another, or induce the EMF in another coil. That's mutual induction. Coefficient of mutual induction, this phi is equal to mi, where m is the coefficient of mutual induction. See, this coefficient of mutual induction have same importance in EMI or in AC as that of resistance. For resistor you have resistance. For capacitor you have capacitance. For a coil you have coefficient of mutual induction. So just like resistance, capacitance, you have another term, that is mutual induction. Note down. And tell me when you stuck somewhere. Tell me once you have written. Huh?
Sir, can you scroll up?
Any doubt, Arpit? Anshika?
No, sir.
सर पर अगर की ओपन है तो फिर करंट कैसे फ्लो करेगा?
When you just open the key, then current decrease from a maximum value to zero value. After some time, the current becomes zero, flux becomes zero, induced EMF becomes zero. But during the time when your current is decreasing from maximum value to zero, there is some change in flux and some induced current. Okay.
सर बट ओपन जब की ओपन होती है तो
Current, see, initially your key was closed. Huh? Initially key was closed. Some maximum current was flowing through the wire. When you just open this key, then current will be zero, but it will decrease to zero gradually. It won't be instantaneous. Like you switched off you open the key and your current becomes zero. Current will take some time to be zero. So if the maximum current was 2 ampere, it will become 1.9, 1.8, 1.7, then it will become zero. So during that whole duration, your flux will change.
ओके सर कैन स्क्रॉल फर्स्ट यस सर
Cephala, if I'm writing M21, that means current is inducing in which coil? In coil 1 or in coil 2?
2, sir. Sir, can you scroll up? Yes, sir.
Abid, I've shared the link in the chat room. भाई ऐसा मत करना है कि तुम उस लिंक के सहारे तुम नोट्स ना बनाओ, बिकॉज यू डोंट राइट ड्यूरिंग द क्लास, तो आपने कुछ भी नहीं सीखा. If you don't
Sir, I
take,
do write, but sir, like I
हाँ
usually
हाँ
get
फिर
late.
सही है, फिर सही है. That's a different issue. But when you are in class, you should take notes.
So where did the minus sign go after unit of M?
I'm just, because when you write unit, the negative sign does not affect unit. So I'm just ignoring the negative sign when I write. Negative sign will not affect the unit of M. Yes, everyone have written up to here? Everyone have written, no? Okay. The next is, there's a one marker question, the definition of 1 Henry. So see how we define 1 Henry. We know that induced EMF is MDI over dt. This is the expression of induced EMF, MDI over dt. From here, you can write that your M is, it's E by, your M is E by di over dt. Yeah? It's E by di over dt. So if rate of change of current di over dt is 1 ampere per second, and due to that rate of change of current of 1 ampere per second, the induced EMF is 1 volt, then the mutual induction is, it's 1 by 1, which is equal to 1 Henry. So if rate of change of current of 1 ampere per second induces an EMF of 1 volt, then the mutual induction of the coil is 1 Henry. It's a very famous one marker question, define 1 Henry. So 1 Henry means you change, rate of change of current is 1 ampere per second. In 1 second, your current changes by 1 ampere. Then the EMF induced in your system will be 1 Henry. That's the definition of 1 Henry. Just note it down, they'll do some questions. Basically, in mutual induction, you get two types of question. One is on solenoid, another is on coil. Do those. No, it's ampere per second. Huh? It's di over dt is ampere per second. 1 ampere per second, it's per second.
Sir, in the above formula, you wrote that it's ampere per meter.
Above formula, I wrote ampere. Sorry. Should be ampere per second. Sorry. Something like that. Ampere per second. Sorry. Please make it correct. It's ampere per second. No, di over dt, it's current by time, it's ampere per second. Please make it correct.
सर वो क्या लिखा हुआ है, रेट ऑफ चेंज ऑफ करंट ऑफ
1 ampere per second. So if rate of change of current of 1 ampere per second, if you change current at the rate of 1 ampere per second and EMF induced in your coil is 1 volt, then we call it as 1 Henry. Can I scroll it?
Yes, sir.
So this is the first question. The first question, you have to calculate mutual induction of two coaxial solenoid. So two coaxial solenoid means two solenoids having the same axis. Two solenoids having the same axis. So you have two solenoids, solenoid 1, solenoid 2. The radius, the outer radius, oh sorry, the inner one is 2, outer one is 1. Solenoid S2, solenoid S1. So the radius of the outer solenoid is R1, the radius of the inner solenoid is R2, the length of the solenoid is R2. You have to calculate the mutual induction of one solenoid with respect to another. Or you can see this in this way also. See, this is solenoid S2 and the outer one is solenoid S1. So when current passes through the outer solenoid, let's first pass current through the outer solenoid. And if I say this current is changing, then this changing current will induce some current in the inner solenoid. So which mutual induction we will calculate, M12 or M21? Haji. Current is passing through the S1 solenoid, outer solenoid, and EMF will induced in the S2 solenoid. So which mutual induction we are calculating, M12 or we are calculating M21?
M21.
M21. We first write the name of the coil in which EMF induced. Then we write the name of the cause. EMF will induced in solenoid 2 due to solenoid 1. So we will first write the name of solenoid 2, then solenoid 1. M21 we will be calculating. So yeah, the mutual induction of both the solenoids will be same. It's mu naught N1 into pi R2 square. Let's first derive it.
सर जो कॉइल बने उसमें ईएमएफ इंड्यूस होगा खुद?
हाँ, किसमें? फर्स्ट कॉइल में?
यस सर, खुद से इंड्यूस होगा.
That's a self induction, but currently we are not concentrating on self induction. There will be an induced EMF there also. First we will discuss mutual induction, then we will do self induction. But in this there will be a self induction in this coil 1, but we are not discussing it here. We're discussing it in the next section. So we have to calculate a mutual induction. So coil current is passing through the outer coil. I'm just naming some parameters. So let's rub everything up. Just 1 minute. It's a very important derivation. Very, very important calculation for your board's exam. Okay, let's start the calculation. So the current is passing through the solenoid 1. Let's define some parameters. R1, R2. They are radii of R1 and R2 are radii of solenoid S1 and solenoid S2. What is I? I is current through S1. The current passing through solenoid S1 is I. Then we have N1 and N2, number of turns per unit length in solenoid S1 and S2. Number of turns per unit length in solenoid S1 and solenoid S2. Then you have L, which is the length of both the solenoid. L is the length of both the solenoids. Length of solenoid. Okay, now let's calculate. Let's first calculate M21. Mutual induction of solenoid 2 means EMF will induced in 2 due to S1. First of all, let's calculate magnetic field. Solenoid C, current is passing through solenoid 1. So solenoid 1 will generate magnetic field. Magnetic field of S1. Yes, what is the expression for the magnetic field of S1? Solenoid 1, Noha. Solenoid 1 will generate some magnetic field. How much was the expression of that magnetic field? Noha Akhtar, formula for that magnetic field.
So mu naught 4 pi I.
Not 4 pi I. Solenoid, Minashi, magnetic field of a solenoid was the expression. No answer, huh? Anshika? Anshika, you were preparing for exams, huh? So what is the formula for the magnetic field for a solenoid? Akshay, Nabil.
Sir, mu 0 into NL into pi r square.
Nah.
into
Magnetic
mu
field
zero.
for a solenoid is mu naught
Mu naught
Ni, na?
Ni.
Mu naught Ni.
Mu
So outer solenoid will generate some magnetic field. So if I show the cross-sectional view, means this view, then it will look like this is solenoid S1 and this is solenoid S2. Radius of the S1 is R1. Radius of the S2 is R2. Current I is passing through S1 and this current will generate some magnetic field. Current will generate some magnetic field inputs. So magnetic field is passing through solenoid S2 also. So I will first calculate flux through each turn of solenoid S1, S2. Let's call this as phi 2 prime. This is the flux linked with each turn of solenoid S2. How will you calculate that flux? Flux is magnetic field multiplied by area. So magnetic field into pi r2 square. Because flux is passing through solenoid 2. In this whole area of solenoid 2, you have some magnetic field. So it's V1 into pi r2 square. That is equation. Now what you can do is you can substitute 1 in 2. When you substitute 1 in 2, you get phi 2 prime is B1, which is mu naught Ni into pi r2 square. That is equation number 3. Next, what you can do is you can calculate the total number of turns in solenoid. See, small n1 and small n2 are number of turns per unit length. The total length of the solenoid is L. Next, we need total number of turns. Total number of turns in S2, solenoid S2. Arpit, what will be the total number of turns in solenoid S2? N1 and N2 are number of turns per unit length. So what are the total number of turns in S2? No answer. Yashika? N1 and N2 are number of turns per unit length. I am asking about the total number of turns in solenoid S2.
Sir, n into L.
The total number of turns will be N2 multiplied by L. N2L. Fourth equation. And let's call this as some capital N2. Some capital N2. And that N2 will be small n2 multiplied by L. That's equation number 4. This is mu naught N1I. N1I. First. Now, total number of turns or total flux linked with S2. Hishma, flux linked with each turn of solenoid S2 is this. The total number of turns in the solenoid S2 is this. Then how will you calculate the total flux linked with X2?
Flux into N2.
Very good. It's N2 multiplied by 5. Is it clear? This is the flux linked with 1 turn. These are the total number of turns. So what will be the total flux? Just N2 into 5 prime. That's equation number 5. Next, what you can do is you can just substitute this 5, or you can substitute 3 and 4 in 5. So when you substitute 3 and 4 in 5, just one second. So you can substitute 3 and 4 in 5. So when you do this, the total flux becomes N2, which is N2L, multiplied by phi 2 prime, which is mu naught N1I pi r square. Mu naught N1I pi r square. That is equation number 6. The next is M21. It's mutual induction of 2. It's mutual induction of S2 with respect to S1. So you can write this phi 2 as M21 multiplied by I. It's M21I. From 6 and 7, you are calculating the same flux. The only difference is when you write 6, in 6, you are calculating flux using magnetic field into area. But in 7, you are using the definition of mutual induction that phi is equal to Mi only. You can equate 6 and 7 because in both, in 6 and 7, you have same flux. So you can simply equate equation number 6 and equation number 7. So when you equate them, you will get the value of mutual induction. So when you equate 6 and 7, equate 6 and 7, you will get M21I is mu naught N1 N2 pi r square Li. So this I will cancel this I, and you will get M21 is mu naught N1 N2 pi r square. So this is the mutual induction. See, mutual induction depends upon number of turns geometry, radius geometry, length geometry, mu naught. medium. So it depends upon these terms. We'll calculate M12 also, but first write these calculations. Note it down. Then we'll see what will happen when you pass current through the second solenoid and you want to calculate mutual induction of the first solenoid. There's a principle known as principle of reciprocity, which says M12 and M21 should always be equal. Reciprocity, theorem of reciprocity, but that's not in your syllabus. But we can still derive that, and when we calculate M12 and M21, they comes out to be. Just have you written up to here? Can I scroll it further?
Just a minute.
Any doubt up to here? Alia, Munib,
No, sir.
Nabil Khan?
No, sir.
Done, sir.
Sir, can you scroll up a little bit? Sir, can you scroll up? Sir, can you scroll up?
I'm saying this question along with a small numerical is usually a 5-marker question in board.
Sir, in the
Yes.
fifth chapter, the dipole and uniform magnetic fields, is it there? Or
Sorry. What are you saying, Ahmed? Maybe?
sir, in the fifth chapter, the dipole and uniform magnetic field, is that part there?
Yes, sir.
Because
Is it there? We haven't done chapter 5th yet, huh?
yes, sir. No, sir. Because in school, whilst they were teaching it, the teacher said that she wouldn't teach it because some parts like that were omitted. Just wanted to confirm.
I'm not very sure whether it is omitted. I have shared that the omitted portion with you. That's not fully omitted. That is still
Yes.
there. But usually teachers skip that topic because that's the exact repetition of whatever you did in electrostatics. Exact repetition of electric dipole. Line by line, word by word. Just instead of P in electric dipole, you're using M here. Instead of electric field, you're using magnetic field. Otherwise, each and every calculator is the same.
No, sir. There's something else. Sir. There's like when I d square theta by dt square is equal to minus md theta. Sir. Sorry.
That's basically torque. Huh? Torque is MB sine theta, right?
Yes, sir. Then what is I into d square theta
It's
by dt square?
it's I into alpha. Torque, the relation of torque is moment of inertia into angular acceleration. That's MB sine theta.
Okay, sir.
Angular acceleration, you can write d omega over dt.
Yes, sir.
Okay, Noah, no issues.
Sir, could you just scroll a little bit up, sir?
Mhm.
Sir, in the link which you sent, sir, for the notes, which one is our batch's notes, sir?
All, I shared the whole notebook with you. So these are chapter wise. Huh? Okay, this is there. Okay. These are chapter wise, like electric charge, then you have electric potential, capacitance, chapter 2 revision, chapter 3 current, magnetics, all EMI. This is your batch only.
Yes, sir.
Uh, and one more thing, many students have exams in this week. So they send a request to end the class at 10 p.m. Like to not to continue that J portion right now. They can't concentrate on it. Because the J portion is not a part of your school exam. It won't come in your school exams. So for today, I won't take that potentiometer thing. You can prepare for a school exam and I will start that topic again. Yes, written.
One
Everyone
more,
have.
sir.
Okay, by reciprocity theorem, you can say that M1 will be exactly equal to M21. Both M12 and M21 are equal. Both are equal. Okay, written. So that was about mutual induction. The next class will start self-induction. So self-induction is the last topic. After self-induction, there is one small thing, induced electric field. So most probably we'll finish this chapter in the next class and we'll start with AC. And once the AC is over, we'll